Hi there. In this video, we're going to talk about principal component analysis. We're going to firstly talk about what it is and why it's so useful. Then we're going to talk about the actual method itself and how that method actually works. And then we're going to go through a detailed example which shows each step of it. And I think that the main point that's going to be so valuable in this video is the fact that we're going to understand how each step actually works and how it ends up being so useful. So when we work with data, especially in today's world, we can encounter many data sets with hundreds or even thousands of variables. So it may seem that having more data is better, but often it's actually too much and it makes the analysis harder. So we're just going to consider this visual on the screen here where we imagine we collect climate data from different weather stations around the world. So each station actually records a large amount of variables. So let's just write some of these variables are. We can have temperature in a certain region, maybe the pressure, and then the humidity, and the wind speed, and wind direction, maybe even solar radiation, rainfall, maybe the amount of cloud cover in a certain area, then perhaps the level of visibility in that area, and then perhaps the dew point of the air. So this is actually 10 variables that we can use. And let's just say we take all this information from the weather stations around the world and we develop some kind of model from it. Let's just say it's a machine learning model. And then using this data, we output some kind of result from it. And this result could perhaps be global trends in the weather patterns. Why the weather is the way it is. Perhaps even, climate trends. So let's just say that, we collect data from 500 weather stations around the world. So we have 500 weather stations. And we have 10 variables. And let's just say we collect this data every day. So we have 365 days in a year. So if we multiply this together, we're going to find that we have 1,825,000 data entries. And this is a huge number. So you can see that it's probably going to be a bit difficult to work with that many data points. We probably need to have a lot of storage, data storage. We probably need to have a lot of computing power to be able to do all of these things. So where principal component analysis comes in is that it allows us to reduce this complexity. And what it does is that it identifies a smaller set of variables which can explain the way our data behaves. So let's just say we can reduce our data set. So our output is still the same thing. We still want to have climate trends come out of this whole thing. But instead of these 10 variables, we now have 3 variables. And these 3 variables are basically called principal components. So we can have principal component 1. So principal component 1 could possibly refer to the global temperatures. So perhaps another principal component could perhaps be seasonal variations. So when we talk about seasonal variations, it could be actually a combination of these different variables. Maybe if we combine temperature and pressure and we check on it throughout the year, we can actually identify certain changes in seasons and that can tell us certain trends in the data. So a principal component, so we'll call that PC2, that could actually be some kind of combination of these variables. And perhaps a third variable could be, or a third principal component, PC3, that could refer to wind patterns. Maybe if we combine wind speed and wind direction into one variable, we could get something like that. So the whole point here is that these variables reduce into something that we can work with. So instead of having 10 variables, we can now replace this with 3, and we can see that the number of data entries reduce quite substantially. But why does this actually work? What is the basis upon which these variables are reducing? Well, firstly, we can realize that some of these variables are interrelated. So we have too many variables. So perhaps temperature and humidity are related. Maybe we can capture them into one variable. So another thing is maybe we have, redundant variables. So there's a difference between having too many variables and having redundant variables, but they are related. Too many variables refer to the fact that some of these variables are interrelated. Redundant variables mean that perhaps some variables actually refer to the same thing. Then we could also have noise. So noise refers to data that's perhaps not really that reliable. For example, let's just say in one weather station around the world where we have some kind of tree that has grown and has blocked these weather stations. That is somehow affecting the data that we're getting. So that means that that particular data set is not reliable. So we have to somehow be able to remove the noise from all of this. So we can reduce these large data set to this smaller data set, and perhaps this smaller data set actually captures maybe even 90% of how our data is varying and capturing what we're actually trying to check, which is that of climate trends. So before going any further, I want to give an overview of what is variability and why it's so important in principal component analysis, because we have to understand the role that variability plays in allowing us to reduce the number of dimensions or reduce the number of variables. So what we're going to consider is a particle that is moving in 3D space. So we have this X, Y, and Z plane. So this is the X axis, and this is the Y axis, and this is the Z axis. So let's just say what we do is we track a particle and where it is. So let's just say at the start of a certain time period, this particle is at the origin. And then 1 minute later, we find it's maybe somewhere there. And then another minute later, we see that maybe it's here. And then maybe another minute later, it's there. And so on like that. So we can see that we can track the positions of this particle along the X, Y, and Z axis. So what are we observing here? If we look at how this particle is moving, we can see that firstly, it's not moving in the Z direction, it's only moving along the XY plane. And we can see that looking in the X direction, we can see that there is quite a significant range of values along the X axis. You can see that it starts from 0 and then it goes all the way up until this last value here. And then along the Y axis, maybe we have some level of variation in the Y axis, but not that much compared to the X axis. And of course, no changes in the Z direction. So let's just summarize that. So in the X direction, we have significant changes. In the Y direction, we have maybe small changes. And in the Z direction, we have no changes. So let's just say we wanted to calculate something like kinetic energy. And we said that kinetic energy of this particle is some function of X, Y, and Z. So we take the coordinates of X, Y, and Z, and we put it into some kind of equation, and we get this particle's kinetic energy. However, we can see that, okay, Z has no contribution to kinetic energy. In other words, it doesn't depend on Z at all because there was no movement in the Z direction. And we can thereafter also see that there was a very small movement in the Y direction, not that much, compared to the fact that there's no movement in Z. So maybe there's a small contribution of the Y position to the kinetic energy. And then lastly, we see that there is lots of changes or significant change in position along the X axis, which means that, yes, this will affect the kinetic energy quite a bit. So it stands to reason that this function is going to depend more on X than it is going to depend on the other variables, because X will have the greatest contribution towards this function. So this is kind of our objective of principal component analysis. At the end of doing an entire procedure, we could find that our most significant axis is the x-axis, and the result could be that we should only reduce all 3 dimensions to this single dimension, this x-axis. But that might not necessarily be the case. The point here is that I wanted to emphasize that variability in a certain direction, in other words, the more something is changing in a particular direction actually tells us how important that variable actually is. So this is where variance comes into play. So variance is something very specific that we have to define and we're going to use in the context of principal component analysis. So let's look at this x direction. What we're going to do is we're going to kind of shine a light on this positions that we have just identified, and we're going to project those points onto the x-axis. So if we do that, let's just say this is the x-axis, then we can actually find a mean. So perhaps the mean might be along, somewhere here. So this is where the mean is, along the x direction. So we could identify that on a single axis, as I've just drawn, and we can say, that's the mean. And then we could also then plot the projections of these points on the x-axis. So maybe they might be here, there, maybe even here, one there, and so on. Let me just make it bigger just so that it's more visible. So these are the points that we have projected on the x-axis. And this is the mean. We'll call that mean x bar. So the variance is actually how much do these points differ from the mean, or how far away they are from the mean. So we can talk about the deviation. So the deviation is, let's just say this is xi. So we have xi minus x bar. So this x bar is the mean, and this xi minus this x bar tells us how far away this particular point is from the mean, the deviation. So when we square this, and then we do it for all the different positions, and then we add it up together, and then divide it by the number of points that we have, then what we get is the variance along the x direction. And that's what it's equal to. Similarly, we can now perhaps project all the points onto the y-axis. Like that. So we can have the y-axis, and perhaps the mean is not in the center as it was in the x-axis, but it's very close to the origin. So this is where the mean is, y bar. And then we have our points clustered around the mean. So in the same way, the variance along the y direction is equal to 1 over n multiplied by the sum of the deviations squared. So the reason why we squared is because of the fact that we need a positive value. So to the left of the mean, we could have negative deviations, and to the right of the mean, we can have positive deviations. So squaring ensures that it's consistent in that we always get a positive number when we sum it up all together. So I said just now that the outcome of principal component analysis could tell us that x is the most valuable direction, and we can see that if we compare the variance of x to the variance of y, that the variance of x is much greater. So this is why we'll be considering it as having a greater contribution towards calculating whatever we want to calculate, like the kinetic energy. However, what about everything in between? What about the interaction between x and y? What if there is a relationship between x and y itself that actually influences our analysis in terms of finding the variable which has the most variance? So there is something that we need to consider where we have to combine the variances of x and y to try and determine this particular relationship. So in other words, we're asking, what if there is another variable that is some combination of x and a combination of y? For example, ax plus by. And this is a variable on its own, for example, u. And this variable u is the one that has the most variance. So how would we be able to determine this? So to start off, what I'm going to do is I'm just going to draw this scatter that's on the xy and just isolate it on the xy plane. So here is our scatter, and perhaps we had a few points like this. So we saw that if we project all the points along the x-axis, we have a variance that's along the x-axis, and we can also project on the y-axis, and we'll have a variance along the x-axis. So the question was, what about everything in between? What if there's another direction here that's between x and y that actually has the most variance? So this is where the concept of covariance comes in. So covariance actually captures the variance between x and y, and we'll be able to use it in a way to tell us if there is a direction that is between x and y, for example, like a diagonal or something like that, which actually has more variance than the variance along x. So the covariance, what it does is that it considers, firstly, xi minus x bar, so that is the deviation in the x direction. Then what we do is we multiply it by the deviation in the y direction, and that gives us a product, and then we sum this product for all the data points, and then we divide it by the number of data points. So what this is the covariance between the variables x and y. So we can see also that if we just swap this around, for example, we put x minus x bar behind y minus y bar. So we asking ourselves, what is the covariance between y and x? Then it's just going to be equal to the covariance between x and y. So another point is that if we find the covariance between a variable with itself, for example, now we take x minus x bar and we multiply it by x minus x bar, and we sum it up and divide by the number of data points, we can see that we're just going to get x minus x bar squared. So which is actually the variance in the direction of x. We just go back up, we can see that this is the formula for variance. So this is just the variance in the x direction. So we now somehow need to combine all of this information, this variances and this covariances and all of that. And the way we do it is by defining and setting up something called the covariance matrix. We'll call that C. So this is the covariance matrix, and it combines all the variances and the covariances in one place. So in the first row of this covariance matrix, we're going to have the variance of x, or rather let's write it like this. We have the covariance of x with itself, then we have the covariance between x and y, then we have the covariance between y and x, and the covariance between y and y. So firstly, we can see that this covariance of itself with respect to x is just the variance of x, and this covariance of y with itself is just the variance of y. And the covariance of y with x, that's just equal to the covariance of x with respect to y. So this covariance matrix has now been set up, and we can now use this to somehow get an indication of the variances in the various directions in this xy plane. So what we're going to do is we're going to firstly realize that we have different directions, the x direction, y direction. We can also have an arbitrary direction. Let's say this arbitrary direction is the unit vector, is always given by the unit vector v. So it's just something random that we have done. So we want to ask ourselves, what is the variance along this random arbitrary direction that we have now chosen? So what we have to do is we have to project this covariance matrix onto this arbitrary vector that we have drawn. You would recall that earlier what we had done was that we had projected the points along the x-axis, and that gave us the variance in the x direction. So now we're going to do the same thing but onto the vector. And what that actually does what it corresponds to is taking the inner product or the dot product of this covariance matrix C with this vector. So let's just write that. So we have this covariance matrix, and this vector, let's just say it has components Vx and Vy. So we have Vx and we have Vy. So we're going to project this covariance matrix on that vector Vx and Vy. So this is equal to this covariance matrix multiplied or dot product with V. So what does this give us? If we just multiply it out, what we get is Vx times the variance of x plus this Vy times the covariance of xy. Then we have in the second row, we're going to have Vx times this covariance of xy. Then we're going to have plus Vy times this variance of y. And this is a vector, and it's a 1 by 2 vector, so we have 2 rows here. So the next thing that we're going to do is we're going to multiply this column that we have by the transpose of V. So why are we doing that? We're doing that because it's going to tell us what exactly is the variance in that direction. So if we just analyze what we have just written here, we can see that we have in the first row, we have Vx and Vy, and what it's doing is that it is scaling, or it's a weighted residual, or rather not residual, but it's weighting the variance and covariance. So it's weighting these variances in this particular direction using Vx and Vy as the weighting factors, so to speak. So if we now take this vector that we have and we multiply it by the transpose of V, let's just see what we get. So that's what we're going to do. So we have this C times V, and what we're doing is now we're taking the dot product with the transpose of that. So this transpose vector simply becomes Vx, Vy. And now we multiply this out. So we're going to have this row times this column. So it's going to be Vx times Vx, that gives us Vx squared, times the variance of x. Then we're going to have plus Vx times Vy times this covariance of xy. Then we're going to have Vy times Vx. So it's going to be Vxy, Vxvy times this covariance of xy. And then finally, we're going to have Vy times Vy, which is going to give us Vy squared times the variance of y. So this is an interesting result. We can see that firstly, this is a scalar. And what it's doing is that it's telling us the contributions of the variances in the various directions. If we analyze this, we can see that this is the variance in the x direction. So it corresponds to what we had drawn earlier right here on the top. So this is the variance in the x direction. And it's being squared, and that's telling us this contribution in that direction. And then also we have Vy squared. So the variance in this direction V is this Vy squared multiplied by the variance of y. Then we have this Vx, Vy covariance xy. So this is just the same thing as writing a 2 in the front here. So we can remove this term and just add it together. And we can write a 2 here in the front. So it's saying that we have a component from the x variance and the y variance, and then we have 2 times Vx, Vy times the covariance. So what this is saying is that this tells us that our variation or variance in this particular direction V depends on the covariance and this components of that direction in this particular way. So this final equation that we have is the variance in the direction of V. So it's in the direction of V. So let's just remember what the entire point of this exercise is. The entire point of this is that we have now established that variance matters quite a bit, and where the variance is maximized or where the variance is the most tells us the importance of a particular variable or a combination of different variables. So we have variance in the x, variance in the y, variance in between, and now we have determined a formula that can tell us the variance of a combination of these variables. So this direction v, and now we have some equation that tells us this. So the objective of principal component analysis is to tell us which combination of these variables actually gives us the maximum variance. So we want to find a direction, so I'm drawing multiple directions here, that tells us where is the maximum variance. Which of these directions actually is the maximum? So if we go back down to our equation, what we're doing is we have this relation. Now V transpose some arbitrary direction times this covariance matrix times this direction of this vector we're considering, and we want to maximize this. So that's what we want to do. And we have a constraint. Earlier on we said that this vector v is a unit vector, so it has a magnitude of 1. So what that means that if you take the transpose of the vector and multiply it by the vector, you should get 1. So this is a system of equations that we can solve, and specifically we can solve it using Lagrange multipliers. So I'm not going to go into the mathematics of Lagrange multipliers. I've done a video on it previously, so you can go back to the playlist on multivariable calculus and watch that video. But in any case, what we do is we form a new function that depends on this vector v and some scalar lambda, and we say that this is equal to v transpose times this matrix C times V, and this is going to be subtracted from lambda into V transpose times V minus 1. So where did this equation come from? Well, it's part of the process of Lagrange multipliers. We combine this function, which we're trying to maximize, and the constraint. If we take to the 1 to the other side, then we get this term minus 1, which is what we see here. And this scalar, this lambda, is actually what the Lagrange multiplier actually is. So we're saying that this function minus this constraint times by some factor is equal to 0. Or rather, this constraint is equal to 0. So what we now do as part of the procedure is we take the derivative of this function with respect to different variables. So in this case here, it's going to be v, and we set it equal to 0. So what is the derivative of this term? Well, we have now matrix differentiation. So I think you can go and check up how to do matrix differentiation, but I'm not going to elaborate on all of the details here. You can go and check it up. But the point of the matter is that we have v transpose times v. So in normal calculus, so this would be something like x squared. We can think of v transpose times v as x squared, and we have a constant in front of it. So if we take the derivative of this, we're going to get 2cx. So that's the analogy. So when you find the derivative of this term, then what you get is 2 times the covariance matrix times v, in the same way that the derivative of cx squared gave us 2cx. And finally, we saw that v transpose times v is just 2x, as we had explained here. So what this term is lambda times 2 times this vector, and this is equal to 0. So when we solve this, we find that what we get is this covariance matrix times v is equal to lambda times v. And what does this look like? Well, this looks like the eigenvector equation. I had done a video previously about eigenvectors as well, and I showed how this equation comes about. But we can see that when we solve this particular equation, then we get the eigenvector equation. So what does this mean? This means that if we go back to our plot and try to identify the direction which has the most variance, what we're going to find that it's going to be the eigenvector. So I'll just repeat that one more time. The direction in which the variance is the most is the eigenvector, and how much is that variance specifically is the eigenvalue. So in the problems of principal component analysis, what it boils down to is finding this covariance matrix, then finding the eigenvector that corresponds to this covariance matrix and determining the eigenvalue. And then the actual value of the eigenvalue will tell you the extent of the variance itself. So this is the explanation behind why we actually do principal component analysis in the particular way that we do it. So I now want to complete this video by giving a complete overview of the procedure of applying principal component analysis to a particular system. And what we're going to do is just consider some variables. For example, we just sample 5 people, and for those 5 people we get their height, their weight, and their age, and also we measure their blood pressure. So we want to relate blood pressure to be some kind of function of these 3 variables. But through principal component analysis, we want to see if we can remove these 3 dimensions or these 3 variables and make blood pressure just a function of one single variable that is some combination of these 3 variables. So the first step in principal component analysis is to take this data and to center it. So center it is another way of saying we want to put the deviations of these different columns into a matrix. So we'll say center the data. So that involves determining the mean for each column. So the mean height, so that will be the sum of the column divided by 5. So it will be 160 plus 170 plus 180 plus 190 plus 200. Then this is divided by 5. And this gives us 180. So similarly, we can determine the mean weight. So the mean weight is just going to be 75. And finally, the mean age. So the mean age is 35. When we now say we center the data, we also mean that if it's represented like that, then we can take this and we can center it to be on the y-axis. So it now looks something like that. So the mean of this new data set consisting of these deviations is actually 0. The mean is 0 of the new data set. So I mean, when we take these deviations and we put it into our matrix, and when we determine the mean of that new column, then it should be 0. So let's do that. Let's put these deviations in a matrix. We'll call that x prime. So what we're going to do is we're going to take these values of height, 160, 170, and so on, and we're going to subtract 180 from each one of them. So we'll have 160 minus 180, and then we'll have 170 minus 180, 180 minus 180, 190 minus 180, and finally 200 minus 180. So this is the first column of this matrix. So 160 minus 180 is minus 20. Then we're going to have 170 minus 180, which is minus 10, and then 0, and then 10, and finally 20. So we're going to do the same thing for the remaining columns. We're going to take weight and then subtract the mean, and then finally age and then subtract the mean age. So if we do that, then we're going to get, again, minus 20, minus 10, 0, 10, and 20. And then for the age column, it's going to be minus 10, minus 5, 0, 5, and 10. So the second step is to now determine the covariance matrix. So let's write that as step 2, is to find the covariance matrix. Earlier on, I'd given the definition as if we have the data point minus the mean multiplied by the deviation of another variable, y minus y bar, and then we sum up each of these and divide it by the number of measurements minus 1. So earlier I may have said 1 over n, so it's the same thing. So we use n minus 1 if we're talking about a sample from the population. So since this is a sample of all the people measured, their weights, their heights, and so on, then we use 1 over n minus 1. So if we write this equation in matrix form, then it looks something like this. We have this matrix, we call that x prime, and we take the dot product of that with the transpose of that matrix. So it's just a way of writing this equation in matrix form. And then we divide by 1 over n minus 1, and this is the covariance matrix. So let's do that. So this x prime, we have just written that. So that's what x prime is. And now the transpose of x prime, we make the columns the rows. So when we do that, okay, we'll have 20, 20, 10. This is this final row that's been made into a column here. Then we'll have 10, 10, and 5. Then we'll have 0, 0, and 0. And then minus 10, 5, minus 5. And then lastly, minus 20, and minus 10. So I'm not going to show each step of this multiplication. This is quite straightforward. We multiply the first row by the first column and proceed with all of the entries like that. So this is a 3 by 5 matrix. And then this is a 5 by 3 matrix. So we should get a 3 by 3 matrix as the result. So when we do that, we find that this 3 by 3 matrix has the entries 250, 250, 125, again 250, 250, 125, and 125, 125, 62.5. So this is what the covariance matrix is equal to. So 250 is the variance along the of the height, then 250 is also the variance of the weight, and 62.5 is the variance of the age. And then the remaining entries is actually the covariance between the different variables. So the next step, step 5, is to determine the eigenvalues and eigenvectors of this covariance matrix C. So in order to do that, what we do is we solve the characteristic equation. So it's the determinant of this covariance matrix minus lambda times this unit matrix, and we set that equal to 0. So this is essentially 250 minus lambda. Then we have again 250 minus lambda, and then 62.5 minus lambda. Then we have 125, 125, then 250. There's a 250 here as well. And we have 125 and 125. So we're finding the determinant of this, and we're setting it equal to 0, and we are solving for lambda. So I'm not going to show each one of these steps. I've done this in previous videos, so you can just go up and check it if you're unsure of how to go about finding the determinant of a 3 by 3 matrix. So when we do that, we find that lambda is equal to 562.5 So that's lambda 1, and then lambda 2 is equal to 0, and lambda 3 is also equal to 0. So now that we have the eigenvalues, we can go and we can substitute inside the equation. So that equation is, we have the covariance matrix minus lambda I times V, which is equal to 0. So this equation basically is the eigenvector equation. So I covered this in the previous video as well. We essentially have C times V equal to lambda V. And this is where all of this comes from. So when we substitute lambda inside this equation and we solve for V, we get V1 associated with lambda 1. And we find that V1 is equal to 0.816, 0.408, and 0.408. So in principal component analysis, we will have eigenvectors associated with each eigenvalue. And since these eigenvalues are equal to 0, that's lambda 2 and lambda 3, we'll only consider lambda 1 here. But we have principal components. So this V1 is called the first principal component. So this is the first principal component. So we will rank the eigenvalues in terms of size. So the largest eigenvalue would correspond to the first principal component. Then the second largest eigenvalue would be the second principal component, and the third largest would be the third principal component in that manner. So V1 is this first principal component, and it actually shows our new variable. So this new variable that we've determined, we'll call that Z1. So Z1 is actually equal to this 0.816. So we have 0.816 multiplied by height plus 0.408 times the weight plus this 0.408 times the age. So this Z1 is our new variable. So if we were to just show it in terms of the matrix, so here we have our matrix. This is our data set. This is our centered data set, I would just remind you. And then now we multiply this by 0.816, 0.408, and 0.408. So when we do this multiplication, the first row by the column and so on, then we find we get a data set that consists of the values minus 28.6, minus 14.3, 0, 14.3, and 28.6. So this data set is very, very important. So this is our result. Our result is, this is the new set of values of Z. Remember that Z is equal to this new column vector here. And if we go up all the way now to our original data set, which had blood pressure in it. So yeah, so instead of now relating blood pressure to these three different variables, it's now been related to one single variable, that is this Z1 that we had written at the bottom, and it has all those values that we had just written down now. So we can just relate blood pressure to Z1 as one single variable, and this Z1 is a combination of height, weight, and age. So just one other point to mention here. If we do actually make this relationship, we have to ensure that we also center the blood pressure data. So in other words, we take the mean of the blood pressure column, and then we find the deviations, and then using that new data set of the deviations, we then relate that to Z1. So that would be our new correlation. We can do a scatter plot of this blood pressure data against this Z1. So perhaps it'll be BP prime, so this is the centered blood pressure data against Z1. And then we can describe all of the data just on a single plot like that instead of using 3 variables. So this is the power of principal component analysis. So in this video, we covered quite a bit of information. We firstly started off by showing, the value of principal component analysis and how it works. Then we went on to show the actual derivation of why the method is the way it is. So we showed how actually we need to find the eigenvalues and eigenvectors of this covariance matrix. And then we spoke about why variability matters as part of that, because we saw that how important a variable or combination of variables is depends on the level of variation or variance in a particular direction. And then we finally saw that we calculate that variance in a particular direction by looking at the eigenvalues and eigenvectors of this particular covariance matrix which we had derived. So thank you very much for watching.